Hello, Dr. Savich. I'm doing my final as a video format. As you can see, I just felt like explaining these next few chapters over a game I spent a little too much time on. This game is called SMITE, Battleground of the Gods. The reason I chose this game to be the background entertainment was because, like with math, this game I have put in a lot of time and effort to get better at. Granted, this game I have over 1,800 hours on, and that span a couple of years. This game has taught me how if you want to get better at something, you must sit and learn about it to get better, and I have done the same with my math class, and especially yours. So, Chapter 10, Parametric Equations and Polar Coordinates. Chapter 10 was a rough chapter for me, I'm not going to lie to you. The brand new set of equations known as parametrics scared me at first because I was stuck in my normal x and y type of equation, so this was a new concept and I was cautious about it. So the basics of parametrics are that x and y coordinates are now f of t and g of t. In my eyes anyway, I thought of them as two separate equations now. Another cool thing about this chapter was the fact that I learned a new type of shape, a cycloid. I will now attempt to throw a picture on screen. I'm still learning how to edit videos, so wish me luck. We learned how some parametric curves have similar properties to the other curves. The first section of this chapter felt like a breeze, just turning XY equations to parametrics. That's when I remembered, hey, I'm in calculus. We must do something hard with these new toys, and that's when we got introduced to using calculus with the parametric equations. At first, we learned how to take the derivative of these curves. Then came one of the biggest points of the whole chapter. Area under the curve. So here's the equation to that. I don't know what it looks like. I'll find a picture of it, put it up on the screen for you. And with learning the area, you must not forget the arc length formula as well. But with arc length, we had to do integrals, which I may add, I hate doing. They're hard and annoying, and they're a long process. It's just, they're hard. Then came along surface area, which is also a pain because integrals, but hey, math is cool, I guess. After this hard stuff, I thought to myself, man, I hope Dr. Savich teaches us something easy. I was very wrong about that. He showed us the light of Cartesian and polar and how to switch them from going back and forth. Then came doing the stuff we learned in parametric to do the same with arc length and area and polar. So that was fun, I guess. When polar came, weird cardioids that had equations and stuff for them. Oh yeah, they were called conic sections. With these fancy looking graphs, we had learned how to do arc length and such with those as well. So the end of chapter 10 ends here. Wishing I could catch a break. Came a dark and scary chapter 11. Chapter 11, Infinite Series and Sums. This chapter right here is the reason why I'm not in Calc 4 right now. Last semester was rough due to online learning, and I had a terrible, terrible teacher. This chapter, I was dreading this semester because I knew how hard it was and how confusing all the tests that we have to do to find stuff. Whoa, whoa, whoa. I may have jumped too far to the end of the chapter because I got ahead of myself thinking about how bad this chapter was for me. Let me tell you about the pain of this, how the pain of this chapter starts. It all starts with sequences, which is defined as a list of numbers written in a definite order, which I had to look up. Then we are shown a cool little famous, not so famous sequence called the Fibonacci sequence, which basically is each term is the sum of the two preceding terms ahead of it. The person who found this was a guy named Fibonacci from the 13th century who solved this because he was breeding rabbits. Then came the convergent and divergent debacle. All that convergent and divergent means whether or not the series goes to a certain number. Then came series, which is the sum of infinitely many terms. Since it's kind of hard to add up 1,000,000 plus numbers, we use series to approximate the sum of these numbers. One way we do it is through partial sums and taking the estimate of it. Now we got introduced to tests that find whether or not they converge or diverge. The first one of these tests is the integral test, which basically says if you have a function that is convergent then the improper integral of the sum is convergent, and it goes the same way for divergent. Next test we learned about was the comparison test. Definition of this is that if the summation of b sub n is convergent and a sub n is less than or equal to b sub n for all n, summation of a sub n is convergent. The same goes for divergency, but it's a sub n greater than or equal to b sub n for all n. Then we learned about the alternating series test, which is simple. I actually understood how this one worked, surprisingly. Next was the ratio and root test, which was used mostly for testing if it was absolutely convergent, and if it failed that test, it's either divergent or we have to try a different test. Then came the power series, which the series converges when x equals a or converges for all x values. Then lastly, the Taylor and Maclaurin series. These series have actually showed up in my computer classes, so it's a nice refresher for these two panes. This series is basically about using power series in a way to get a radius of convergence or a sum at a certain n value. And that was basically the explanation of why I hated this chapter, but learned to appreciate the math behind these things and get a better understanding for it. Onwards to Chapter 12. Chapter 12, Vectors and the Geometry of Space. I thoroughly enjoyed this chapter. It definitely does not have to do with the fact that I took Physics 1 and just finished up Physics 2. Hopefully I passed that final. Vectors are fun, and they finally introduced the concept of 3D, which isn't really a concept since we live in 3D, but regardless, vectors. What are they all about? First of all, say bye-bye to the x and y plane. We are on the x, y, z plane now. This means a few equations that we know are going to have to change. First is the distance formula for a line. The only change to the formula is that you add in the z1 minus z0 squared to the normal distance formula. Innovative. The mathematicians, which I don't know because I'm not one, it just seems like they make things easy sometimes. And then, anyways, vectors. So scalars are a thing, which all they do is make the vector stretch or shrink based on the number that we're given. It's kind of like the same idea as 2x. It's just a graph of x, just stretched 2 times as long. Learned how to do the magnitude of the vectors, which is the square root of the a1 squared plus a2 squared plus a3 squared. Unit vectors are cool. Unit vectors are a vector whose length is 1. Unit vectors become more important later. Then the dot product came around and gave me a breath of fresh air. Simple and easy. It works the way you think it does. The xyz of each vector is multiplied by the other xyz vector. With learning this brought cross product. Probably my favorite thing I've learned this semester, which is, I think of it as a fun puzzle you get to solve to get either another vector, or you take the magnitude of that cross product you got to get the area of the parallelogram. Well, you remember the parametric and polar stuff from chapter 10? Well, they came back with a vengeance. With these back, we learned how to find parametric equations through using vectors. Then came quadratic surfaces and the long list of equations that followed. Thus concludes chapter 12. So, chapter 13, vector equations. So, this chapter is the last chapter I have to discuss, which is sad. So I'm basically summing up our whole entire semester in under like 13 minutes, I hope. This chapter takes parts from chapter 10 and chapter 12 and merges them into a calculus sandwich. I think it's not a good sandwich in my opinion, but hey, it's just my opinion. First piece of this sandwich is describing curves in 3D space using polar coordinates. Now that we're on to derivatives and integrals with vectors, I was happy with the derivatives. I loved them. Calc 1 was my favorite class of all time. Derivatives, the best. But as I've said before, I thoroughly dislike integrals. But we must push aside our differences for integrals and I to have a better understanding of one another. The good thing about derivatives, though, is that they work as you would assume they would in polar. The difference for integrals, though, in this chapter are that you can separate these integrals into their respective I, j, and k vector integrals. Next, we got the idea of arc length and vector notation. And as you expect, it's the same as regular functions, but just split into each I, j, and k vector values. Next is curvature. Remember when I said unit vectors would be important later? Well, it's later. Curvature is given by the magnitude of the derivative of the unit tangent vector divided by the magnitude of the derivative of the vector itself. Man, that was a mouthful. Then we learned what the normal and binormal vectors were about. The unit normal vector is the derivative of the tangent vector divided by the magnitude of the derivative of the tangent vector. Then, the binormal vector is just the cross product of the unit normal and the unit tangent vectors. And hey, I just summed up 4 chapters in under 13 minutes. I'm proud of myself. So, you thought you could get rid of me that easy? Nah, I'm just playing. So I have a few closing remarks. I just want to say thank you, Dr. Savich, for giving me the opportunity to be in your class and be such a wonderful teacher to the class and myself. I really enjoyed your explaining the reasoning behind the stuff you were teaching us. And it truly showed that you cared about us learning instead of some of the teachers here at OU that just go to the lectures, they talk, they really don't explain much. They just go over the basics, and you can tell that they're not excited about teaching us the knowledge they have. I also want to thank you for being such a kind and compassionate person to the class during this semester. COVID, everyone's being isolated. It's affected me a lot. I felt alone a lot of the times, but during your class, having you this semester, it made me want to sign in Monday, Wednesday, Friday at 2, so I could just hear your teaching. And your class just made my day better and made me feel better, not as alone. So I really do appreciate you being so nice and kind to everybody and being the kind person that you are. And I really did enjoy the art project. Even though mine was you still appreciated it at what it was because it was me and not no one else's. So thank you again for all that you do. I hope you enjoy this. And I think I did this in 13 minutes. I'm proud of myself. Thank you. Have a nice summer. Have a nice career. Take care of your kids. Be a great father. Thank you very much.
Enemy missing left. Be careful, middle.
Enemy spotted. Sing middle. Topple. Follow me.
An enemy has been slain. Enemy ultimate down.
Until next time.
The enemy's at the Gold Fury. Attack.
Until next time.
Courageous beast. Your time
Great
to
effort.
rest has come.
Excellent
Drag them into the depths. The wonderful fruits of my labor.
You just can't be stopped. What the Zeus is going on? Doom
Sapling.
Okay, I see you. You're on a killing spree.
My garden glows.
Your middle tower is under attack. Face the pit.
Okay, what else?
Has ended.
Teammates are on it. Enemies are slain.